The universe is just like so big, and this vast cosmos contains trillions upon trillions of stars. Stars begin their life as interstellar gas clouds that are composed of highly concentrated hydrogen and helium. These gas clouds are formed when the denser clumps of hydrogen and helium particles are pulled together by gravitational force. When the cloud is large enough, gravitational force causes it to collapse in on itself towards the centre. The colder the cloud, the less resistant it is to the gravitational collapse. Now, as it collapses, within the gas clouds are areas of low density and high density. They can get denser and denser, resulting in it getting hotter and hotter.
Molecular cloud, often called a stellar nursery, is a type of interstellar cloud. The size and density of these clouds allow the formation of molecular hydrogen. Molecular hydrogen is difficult to detect by infrared and radio observations, so the molecule that is often used to determine the presence of hydrogen. Stellar nurseries are vast and can be light years across, and through a telescope they are often seen as fuzzy objects, and they come in a variety of shapes and sizes. Stellar nurseries account for less than 1% of the volume of the interstellar medium, but they are the densest part of the medium, having an average density of 100 to 300 moles per cubic centimetre. They have an internal temperature of only 7 to 15 Kelvin. The formation of stars occurs exclusively within molecular clouds. Astronomers believe that nebulae are created from a huge collapse in an interstellar medium, which is made up on gas dust and cosmic rays. The physical conditions of the interior of a stellar nursery are quite different from those of surrounding low-density interstellar medium. In the outer parts of the cloud, hydrogen is neutral. Deeper within the cloud, it becomes colder and darker due to dust blocking out ultraviolet radiation. Stellar radiation can, however, enter the cloud through channels where the dust and gas density is lower than average. In the inner regions of stellar nurseries, we get the formation of stars from the gravitational collapse of dense clumps within a nebula. Initially, the clouds consist of a chaotic jumble of smaller clouds, of which each one is destined to be an individual stellar system. Each system has a rotary motion caused by the original motion of the material that is falling out into it. Due to this rotating motion, the collapsing cloud flattens as it contracts. Eventually, the majority of its mass is rotating near its centre, and a protostar is created. The most common stellar nursery is the photo known as the Pillars of Creation, which lies approximately 7,000 light-years away from us, which was captured by a photograph in 1995.
A protostar is a large mass that forms by contraction of the dense cloud of gas in the interstellar medium. Protostars have about the same mass as the Sun and typically take about 10 million years to evolve. It begins with the core of increased density in a molecular cloud and ends with the formation of a pre-main sequence star. As the cloud of gas continues to contract, it begins to increase in temperature. The temperature increase is caused by the conversion of gravitational potential energy to thermokinetic energy. As a particle falls towards the center of the contracting fragment, its gravitational potential energy decreases and its kinetic energy increases. Therefore, the more the cloud contracts, the more the temperature increases. When molecules collide, they are left in an excited state, which can emit radiation when those states decay. In a protostar, most of the radiation is in the microwave or infrared range of the spectrum. At the early stage of the star's formation, most of the radiation escapes. This prevents a rapid increase of temperature of the cloud. As the cloud contracts, the density of the molecules increases, which makes it more difficult for the emitted radiation to escape. This causes the temperature within the cloud to rise rapidly. As the system evolves, more of the emission starts to come from the protostar rather than the surrounding gas and dust. The temperature increases substantially, and the disk surrounding the protostar becomes smaller than the protostar. Some pre-main sequence stars are difficult to observe, as they have already moved on to the main sequence before they can blow away the surrounding dark nebula.
The collapsing gas and dust burns hotter, eventually reaching temperatures sufficient to fuse hydrogen into helium. The star turns on and becomes a main sequence star, powered by hydrogen fusion. Fusion produces an outward thermal pressure from the hot core that balances with the inward pressure caused by gravity. The energy that is generated at the core makes its way to the surface and is radiated away at the photosphere. A main sequence star will shine steadily for most of its life and gets its energy from nuclear fusion reactions. The process fuses 4 hydrogen nuclei into a lighter helium nucleus. The change in mass is what releases energy during nuclear fusion reactions. A main sequence star will produce energy from hydrogen for millions of years. Larger stars will fuse hydrogen to helium at a much faster rate, therefore giving them a shorter lifespan. When a star runs out of hydrogen and helium, the forces between the outward pressure and the core destabilizes and the core contracts as the star is unable to maintain equilibrium. The core of helium will contract and the hydrogen burning will continue in a shell surrounding the core. Due to gravitational potential energy being lost when the core contracts, thermal kinetic energy increases and temperature increases. Helium fusion then begins, and the star begins to expand. When the outer layer cools, it starts to look a deep red colour, hence the name red giant.
A high mass star will undergo a similar process to that of a red giant. Now, because of their higher mass, when the core collapses, when the star runs out of hydrogen, the increased temperature leads to the fusion of helium extremely rapidly. The energy released by the very high rate of helium fusion means that the star evolves directly into a supergiant. Now, the gravitational force of the star is balanced by its immense outward radiation pressure caused by that helium fusion taking place at the core. Whilst evolving into a red supergiant, the star loses a considerable percentage of its mass. So, while supergiants are the largest stars in the universe, they are not the most massive. A red supergiant appears red due to their low surface temperature, which is between 3,500 and 4,500 Kelvin. Their cores, however, are still extremely hot. Most red supergiants are about 1,500 times the size of our home star, that of course being the Sun. Due to their size and mass, supergiants need an incredibly large amount of energy to sustain them and prevent gravitational collapse. As a result, they burn through nuclear fuel very rapidly.
The red car and the blue car had a race. All red wants to do is stuff his face. He eats everything he sees, from trucks to prickly trees. But good old blue, he took the Milky Way. He's looking for a chocolate treat, fluffy and light, 'cause he knows it's something that tastes just right.
Oh no, the bridge has gone. Old Red can't carry on.
But good old blue, he took the Milky Way.
The life cycle of stars can be plotted on a graph, the hertzsprung-russel diagram. This graph plots the average surface temperature of stars from a high temperature to a low temperature against their luminosity, where 1L is equal to the luminosity of our Sun, which is 3.85 times 10 to the 26 watts. Stars that have a smaller mass, like our Sun, usually evolve into red giants, causing them to move away from the main sequence to here. Over time, the cooler outer layers are lost, resulting in the stars moving across the diagram, crossing the main sequence line, and ending up down here as white dwarfs. Higher mass stars, such as the red supergiant VY Canis Majoris, start up here as blue giants, before speedily eating up their fuel and swelling into red supergiants before going supernova.
When the hydrogen source in the core starts to run out, gravity begins to compress the core, causing a rise in temperature to about 1 billion Kelvin. This causes the star's cooler outer layers to expand and create a much larger red giant star. This causes a rise in stellar luminosity, where the energy is distributed over a large surface area. When the temperatures reach about 1 billion Kelvin, the available helium nuclei fuse to oxygen and carbon so that the star resumes radiating energy, causing it to stop contracting temporarily. The new helium burning phase forms a growing inner core of chemically inactive carbon and oxygen. Above, this is a thin helium burning shell, which is surrounded by a hydrogen burning shell. This burning process throws out the star's outer layers one by one. When the outer surface of the exposed core reaches about 30,000 Kelvin, there are enough emitted ultraviolet photons to ionize the ejected atmosphere, which causes the gas to shine as a planetary nebula. The famous planetary nebula known as the Cat's Eye, located in the Draco constellation, was formed over 1,000 years ago.
After shedding its outer layers to form a planetary nebula, the star will leave behind its core. This forms the remnant white dwarf. Usually, white dwarfs are composed of carbon and oxygen, and are extremely dense. The material in a white dwarf no longer undergoes fusion reactions, so the star does not have a source of energy. A white dwarf is very hot when it is formed, but due to there being no source of energy, it gradually radiates away its energy and cools. The oldest white dwarfs still radiate at temperatures of a few thousand Kelvin. Over an extremely long time, a white dwarf will cool to temperatures at which it will no longer emit significant heat or light, and will become a cold, black dwarf. However, the length of time that it takes for a white dwarf to reach this state is calculated to be longer than the current age of the universe.
If a star is massive enough, the Fermi pressure of electrons is too weak to prevent the gravitational collapse, and in a very short space of time, the electrons are crushed against the protons, forming neutrons, and the core has a very immense pressure. The core will eventually become hot enough to fuse carbon to neon, and then fuse neon to iron. Heavier elements build up at the centre of the star, and the centre becomes layered. Once the core becomes greater than a certain mass, known as the Chandrasekhar limit, the star begins to implode, and the core collapses. The core heats up and becomes denser and denser. When the collapse of the core suddenly halts, it causes a giant explosion called a supernova. A supernova is a stellar explosion that briefly will outshine an entire galaxy and radiates as much energy as any ordinary star would be expected to emit over its entire life. It then fades from our view over several weeks or months. This sudden explosion expels most of the star's material at a velocity of up to 30,000 kilometers a second. This creates a shockwave in the surrounding interstellar medium. A large number of primary cosmic waves come from a supernova.
After a supernova, the core that remains is called a neutron star. This is made up of tightly packed neutrons. A neutron star will have a diameter that is 19.3 to 48.2 kilometers and has a mass that is about 1.5 times that of our sun. So neutron stars are very dense. 1 teaspoon of a neutron star material would weigh about 1 billion tons on Earth. A neutron star is made up of a superfluid gas of tightly packed neutrons. This is surrounded by a solid lattice of neutron-rich nuclei. On top of this is an iron crust. Due to its high density, a neutron star has extremely high surface gravity. Now this results in the surface being very, very smooth. It's a bit like this snow. Now if I pick it up, no, it's not round at all. However, if I compact it down, representing that gravitational force, it not only becomes a lot denser, but a lot smoother and rounder than it was before.
After a supernova explosion, the remaining core continues to collapse under immense gravitational force. The compression by gravity is so strong that it overcomes the repulsion created by forcing electrons together and of compressing protons and neutrons. Gravity compresses the core to such an extent that its density becomes infinite. The volume of the core becomes zero. This state of matter is called singularity and can't be explained by the laws of physics. Yet. The gravitational field surrounding a black hole is so high that no radiation, for example light, can escape from it. This is why they appear black.
The expanding shells that are expelled in a planetary nebula and the material that is exploded by the supernova eventually drift away from where the explosion happened and merge with gas and cosmic dust that floats in the spaces between stars. Sometimes the debris left from a supernova of a star will drift into a stellar nursery and mix with the gas and dust that is in the process of forming new stars, once again starting at the beginning of the cycle.